Welcome to lecture 8-6. We're studying VLSI design. Today we'll solve an example related to rise and fall time delays, and this example will also include the effect of scaling, small m, that we have been discussing from lecture 8.1 to 8.5. In this example, we are giving a knot, a CMOS knot. If we have this CL, this is the output, and if we have a CL is equal to 100 femtofarad, the delay is 123.75 picoseconds. This is rise time delay. But if we increase the value of CL by 15 and it becomes 115 femtofarad, the delay also increases. We already know the delay is directly proportional to CL. In fact, we have studied in chapter number 7, last chapter, that this TR has an equation that is a linear equation of a line. So TR is linearly related to CL. Increasing CL will increase TR linearly. And it is also given that it's a symmetric knot where beta n is equal to beta p. This means kappa n times the aspect ratio of n is equal to kappa p times the aspect ratio of p. So what we are required to find is in step number in part A, we have to find Rp, Rn, and one more thing, CFET. Right. We know that the expression for TR we derived in last chapter and have been discussing from 8.1 to 8.5 is TR0 plus alpha p CL. This TR0 can also be written as 2.2 times Rp CFET plus alpha p is 2.2 times Rp times the CL. So let's put the value of TR and CL in this equation. TR is 123.75 pico means 10 to the minus 12, where CL is 100 femto. This is 100 femto. Femto means 10 to the minus 15. Right. In the same equation, if we put this 138.6 picosecond as TR, this gives us 2.2 Rp CFET plus 2.2 Rp times this CL. So for this CL we have this delay, for this CL we have this delay. Now, luckily we have two equations, 1 and 2, and two variables Rp and CFET. We can solve them linearly to find the value of Rp and CFET. In my notes I have solved or not solved. I think I have left it for the students. Rp comes out to be. This linear solution gives us Rp equal to 450 ohms and CFET equal to 25 femto. So this is the homework for students, to solve these equations linearly and reach to these answers. In step number 1 we have, in part number 4a, we have computed Rp and CFET by solving two equations simultaneously. And the two equations are linear equations. In part B, we need to find out, oh yes, we have to find Rn. Since it's a symmetric knot, Rp is equal to Rn, or Rn is equal to Rp, because it is symmetric. So Rn is the same as Rp. Right now we have to find a general equation, a general expression for Tr. Tr is 2.2, and we have to plot Tr versus Cl. 2.2 Rp, that is 450, times CFT, which is 25 femto, plus 2.2 times Rp, which is 450, times Cl. So this gives us a linear equation, which is 24.75 plus 0.99 Cl. So this is a general equation of a line. If you plot it versus Cl, plot dr versus Cl, this gives us a straight line where y-intercept is 24.75, and it goes on linearly. In step number, in part B, we are also required to find Tf, and Tf is the same as Tr because it is symmetric. The last step, step number C, the last part C. In part C, we are given that now we have to work with a scaling factor m, which is equal to 3 by 2, and we have to find the new value of Tr. Tr is, you already know that Tr for m is equal to 3.2. The first term is independent of scaling because it involves two terms, a resistance and a capacitance. The resistance term is inversely proportional to m, and capacitance is directly, so multiply and they cancel the effect, and this Tr0 remains the same. Plus this alpha p is divided by m, 3.2 Cl. This we have studied maybe in lecture number 8 too. So Tr for m is equal to 3.2 is Tr0, 24.75, the same, remain unchanged, plus alpha p is 0.99 over 3.2 Cl. So 0.99 over 3.2 gives us 0.09. 3.09 Cl. So this is a general expression for a knot which has a scaling factor 3.2. This means the aspect ratio of each transistor is increased by 3.2. In the upcoming lectures, we'll keep on studying more stuff and more examples from chapter number 8. Thank you.